Appreciate it.
Good afternoon. I'm Mike Klein, MSTA Board Treasurer and Conference Committee member, and I'm excited to have the opportunity today to introduce Dr. Desmond Murray for our afternoon's keynote address. Before I do that, though, I'd like to take a moment and say thank you to the dedicated sponsors that helped to make the MSTA conference a conference this year. We're excited to be with you virtual, hoping next year to be back in person, but we're thrilled we could be with you today. So a special thank you to our sponsors, the Michigan Space Grant Consortium, Square One Educational Network, Michigan Sea Grant, Wayne State University College of Liberal Arts and Sciences, the Ecology Center, and the Dove Academy of Detroit. Thank you for your dedication to helping support the future of science education in Michigan. So now, let me tell you a little bit about Dr. Desmond Murray. Desmond Hartwell Murray is Associate Professor of Chemistry at Andrews University, chemistry instructor for Berrien County Math Science Center, founder of Building Excellence in Science and Technology, and the lead editor for and chapter author in the 2016 American Chemical Society Symposium book, The Power and Promise of Early Research. Dr. Murray earned a Bachelor's of Science in Chemistry from Andrews University in 1985, a PhD in Chemistry from Wayne State University in 1992, and was a postdoctoral fellow in chemistry at Harvard University from 1992 to 1994. In 1995, he became the first Black professor of chemistry at Andrews University, teaching and researching in the very building that was dedicated in 1974 by the late Dr. Eric E. Williams, the first prime minister of the country of his birth, the twin island nation of Trinidad and Tobago. He was honored by the Michigan Science Teachers Association in 2012 with the College Science Teacher of the Year Award. Here to share with us his presentation, Building on Young Children's Curiosity, Lessons from the Solid Start Project, I give you Dr. Desmond Murray.
Okay, very good. Thank you very much, Mike.
Thank you.
So, just wanted to start with personal information. I was born on Mole Day, October 23rd, 1023. I don't necessarily believe in numerology, but some people think that I was destined to be in chemistry. Anyway, I want to thank the organizers of the 68th annual MSTA conference for the invitation for me to be part of these proceedings. My objective here is first imagine different and expect amazing. I believe it's not good enough for us to simply reimagine science education. We must imagine different and expect amazing. So I will use my own story as a model of both imagining different and expect amazing.
They can't do it. They're just too young. They lack knowledge.
They can't do it. They can't. No skills. Too young. Give us a chance. No, we're not too young.
Too young.
No, we are not too young.
They can't do it.
They're just too young.
Just too young. They don't understand. Too young. Just too young.
We can do this. We can learn.
They can't do it. They can't do this. They're just too young.
We can do this. Give us a chance. We can do this.
Too young.
They're just too young.
No, we are not too young.
not too young to research.
Okay, we need to get back to the slides. The slides were up. Mike? Okay, here we go. Back to the slides. Good. So, all right. So for the last 25 plus years, I've taught both high school and college at the same time. So a typical day in my life here at work is, seeing both high school and teaching both high school students, undergraduates, and graduate students. So over these years, this has provided me with a unique niche to create seamless, synergistic, what I call interlevel research opportunities for students at all these educational levels. So that research that's done at one level serves as the basis for further research at another level and creates this sort of interlevel collaboration and research feedback. So I think all of us are familiar with the term interdisciplinary. We all use that. We understand what that means. But we never really, or at least rarely, talk about collaborations between academic levels, between, for example, high school and college, which is what I will focus on today. So I use the term interlevel to represent that type of collaboration, that type of work. It's basically in the interface between high school and college. So here I wanted to show that the research from the perspective of curiosity, research is a flat world. To me, that means that real research can be done at both the secondary and tertiary levels, and that curiosity is our admission ticket at any and all levels of research. In fact, the English word research comes from the Middle French word called recherche, and it simply means to go about seeking. There are no restrictions on that definition, to go about seeking. We all can, we all do, and in fact, it is a human birthright. We seek to find, we seek for knowledge, we seek for survival. No PhD is required to seek. Curiosity is our sole and fundamental prerequisite to life. Indeed, one can guess or conjecture that without human curiosity, the universe itself does not know itself. So, what are some other scientists saying about curiosity, science, and research? Here are some examples. Albert Einstein: I have no special talent. I am only passionately curious. I think some of us will beg to differ on how he describes himself as no special talent. But the point is, he saw himself as mostly passionately curious. I'll go to a chemist, 1981 Nobel Prize chemist, Roald Hoffman. In an interview, what sets scientists apart? Hoffman replied, first and foremost, curiosity. A 1986 chemistry Nobel Prize winner, Dudley Hirschbach. Every little child is a natural scientist because they are naturally curious. That's what science is. And we also know that over the centuries, many philosophers and educators have spoken about curiosity, starting with, as an example, Aristotle, all men naturally desire knowledge. John Dewey said the teacher's, at least in one quote, task is rather to keep alive the sacred spark of wonder and to fan the flame that already glows. More recently, Peterson and Seligman wrote in one of their articles, curiosity may be the most foundational aspect of learning. So here, what is, I think, important before I even get into what early research, at least how we define it, is that this idea that is, I think, pervasive in science education, that students must be proficient in reading, writing, and counting before they do science or do research, I would propose that is misguided and mistaken. I think that based on the accumulated scientific evidence that's out there today, children at a very early age are in fact thinking and acting like scientists even before they could read, write, or count. And there are papers, books, research articles on this. So early research, what is it? How do we define it? So the working definition we have for early research is authentic research done before graduate school by high school students, community college students, college freshmen, and sophomores in the curriculum as well as non-curricularly. So one of the things to observe here is that early research based on this definition is cross-demographic. It's regardless of gender, race, disability, socioeconomics. It is cross-demographic. But another thing to note is that while early research is definitely correlated to age, age is not determinative. So, for example, community colleges, where students are probably on average, at least this is what I found from national statistics, average age of about 29, are generally older, but many of them also have not been introduced to research. And so even at 29, early research engagement is something that community college students could be involved with. That's a very important thing because 49% of US graduates earning bachelor's in science and engineering actually attend a community college. So our definition of early research also covers community college students as well. And we talk about that in very much detail in our book, The Power and Promise of Early Research. And we do have handouts. The very first chapter from that book and the last chapter, I believe, also from that book is part of the handouts we have along with this lecture. So I'd like to do a little description of academic research in a way that maybe is kind of familiar to chemists. I'm using the idea here of, I'm thinking about academic research as quantized energy levels. So here you could see these quantum levels, high school at the bottom, the 2-year, 4-year, and then grad. So what is immediately apparent in looking at it from this perspective is that there is a huge quantum gap, if you will, between graduate level research and everything else. So to me, this gap represents 4 things. One is an expenditure. It's very easy to go to the National Science Foundation statistics and find that basically the funding and expenditure and grants that are given out are mostly for graduate research. Some for undergraduate, but hardly any for high school, for example. So the expenditure gap between basically the traditional graduate school, graduate level research dwarfs the research done and the expenditure and investment in early research and in early researchers. For example, in Michigan, using 2010 data, which I don't think has changed much though, the universities and colleges in Michigan spent over $2 billion in research. And so my question is how much of that actually went to early research in any form? Early research, again, meaning high school students getting involved in research, community college, or sophomores and freshmen in college. Basically, in terms of expenditures, that category is pretty much non-existent. If you look at any statistics from the NSF or so, you wouldn't find it. The other thing that this represents to me, this gap, is a waste. It's a waste of human talent and potential. It also represents obstacles. The obstacles are the prerequisites that we place that delays students from doing real research. And it's a loss. It's a loss because it's a loss in research productivity, because high school kids could actually push back the frontiers of research. And so it's a loss. There are obstacles, it represents waste, and it shows the great gap in expenditure. So hopefully you would realize then that early researchers and early research are probably then, based on what we just discussed, the most historically underrepresented and under-resourced demographic in STEM research. To give even more of a history lesson, I'm not going to go through all of this, but it took a while for the US to come up to speed, for example, with Europe. Over in Germany back in 1810, undergraduate research was established. Then in the US, it was not until 1969 that the first undergraduate research program was established at MIT. In 2007, I believe that this is when community college undergraduate research initiatives was started. So research at the community level is something that's growing now. And as far as I know, there isn't a whole lot of investment still in research, authentic research at the high school level. So I think today our challenge in reimagining science education in Michigan and in the United States is to imagine different and broaden science education to include early research and early researchers. And one of the things I want to emphasize on this slide here about why early research, again, is something that I've said before, which is that I believe that to delay research engagement is educational malpractice, because the fact is we know better. The research out there on human development and so on, we know better. To delay research is, in fact, in my opinion, educational malpractice. Going back again to what I said earlier, It is known that before we read, we write, or count, we actually go about seeking. We actually are engaged, curiosity driven. And so for me, research is fundamental. What I like to challenge us is not just to imagine and imagine different, but to imagine big. So, one of my dreams is to have universal adoption of early research. And think about it this way: there are roughly about 16 million high school students in the United States, about 21 million college students, 10 million.
Dr. Murray, I don't know if you can hear me. We lost sound for a second. Dr. Murray, I think your sound is muted. Can you check to make sure we didn't accidentally hit a mute button up above on the top? Or, Amber, can you by chance help us with that? Is that a box you can check?
Yep, I am looking into that right now.
Thank you, everyone. If you'll stay with us for just a minute, we'll get this figured out. While we're waiting for that to come around, I'm really excited to continue to hear what Dr. Murray has to say. I love this. I love this idea of, we know better, imagine different, imagine big.
Yes.
Pretty great. There we go. I think we hear you again, Dr. Murray. I think you're back. Yep, we're
Okay,
back.
all right.
Go ahead.
Okay. Okay, very good. So around the state of Michigan, there are a number of math science centers, and I happen to be teaching at one, instructing at one, the Berrien County Math Science Center. I think that the math science centers actually are a perfect niche market for adoption, implementation, modeling of early research. It cannot be done. I'm not proposing that everyone does early research in the way that I'm doing it, because I have a unique situation where I teach both college and high school. But I think still the idea of early research is something that could be adopted in our math science centers across Michigan. One of the ways that I kind of think about early research too is, we talk about innovation, an innovation society. I think of these early research opportunities as incubators of innovators. It's not simply about the innovation, but about being able to develop the students and the innovators for the future. And so I sort of coined that phrase, incubators of innovators. And in fact, another way to think about it is that they can be effectively early research high schools. So we are all familiar, for example, with research universities. Okay, that's a terminology that's well known in education. So what we are proposing here is early research high schools, early research community colleges. So I think that's one of the things we have to do. If we look at the ideas that are embedded in early research and the objectives, for example, of MySTEM, and the MySTEM vision statement, The pillars of my STEM: create a STEM culture, empower STEM teachers, ensure high quality. I believe, points 1 and 4, especially creating a STEM culture and ensuring high quality STEM experiences, are very closely aligned with the idea of early research. And just to say a little bit about the item number one, the pillar number one, that involves creating a STEM culture. It's a culture where facts are agreed upon, evidence is valued, and conspiracies and alternative facts are rejected. Uh, can can we agree that 1 plus 1 is 2, that atoms are the building blocks of the universe, that each day is actually 24 hours long, regardless of politics or religion? They are not two sides to scientific facts. We need to, in creating that STEM culture, be able to pass along to students the idea of valuing evidence. That's one of the things. Even if these students do not become scientists, as a culture, it's important for us to understand throughout the culture that evidence has to be valued. Um, what I like to focus on now is a little bit of how and when I got into starting early research. I started basically back in 1998 with introducing early research into my sophomore organic chemistry class. Um, and the take home from this is really that over the years, the introduction of early research into my classes has been slow. I didn't try to do everything all at once at the start. It began with 2 weeks of independent research, then a month, the next year, another a month. Then we went to half a semester. And then we finally got to a full semester of full blown, full spectrum, real, authentic research. So after I gained confidence in doing that at the college level for my sophomore organic chemistry class, then we also started a research program during the summer for high school students. And then in 2006, began doing early research in grade 12 at the high school level. Again, began with 2 weeks, a month, half a semester, and then the full semester. So it was short periods of time, slow development. And so if you or anyone wants to get into early research, I don't advise that you try to take whatever you're doing right now and totally change it over all at once overnight. Then in 2015 was also another significant milestone in which we started doing interdisciplinary. So I work very closely with my colleague in biology, Denise Smith. She's a cancer biologist by training. And so now our research program for grade 12 is first semester, fall semester. We have them doing organic chemistry, organic synthesis. In fact, the next slide shows the organization here. It's a full year of research for the grade 12 students here at Berrien County Math Science Center. They can get college credit for this year. Chemistry is in the first semester. We focus on making compounds. And then in the second semester, we focus mostly in collaborating with my colleague, Dr. Denise Smith, in biology on biological activity. So we've had students do things like cancer research based on the compounds that they've made, antibacterial, antifungal, pesticidal, any sort of biological activity that we could think of using the compounds that they made. So students are always happy to know that they, in this class, don't have a bunch of tests, just one exam. At the end of the first semester, there are a number of lectures to get them into becoming independent researchers. We cover things like information retrieval, functional groups, spectroscopy. A lot of things actually that I teach my college students are taught to the grade 12 students. For example, my grade 12 students know exactly how to, it's routine for them now to take IRs and NMRs. They know how to do refluxes. Everything basically that my college students do, my high school students do. They may not have a full year, a full semester of in-depth organic chemistry, but they would have been taught enough in the first few weeks of our course that they would be able to understand what's going on in their projects. Some of the research projects involves agglutinators, hybrid drugs, hybrid pesticides, sensors, and so on. The course requirements include having to write a technical paper, a normal research report, do a poster presentation. I also encourage them to do public science, and we'll talk about that here pretty soon. And they are also required to do an oral presentation. This here just also summarizes across both levels, high school, undergraduates, some of the themes and projects that they are involved in. My training was in organic synthesis, so naturally that's the major area of research in chemistry, but there are different themes that we work in and our students work in. This particular slide is to emphasize again the interlevel. This gives you at least 12 different research topics, research projects, in which the research is done by students at the high school level and the undergraduate level. And the case is that it's a feedback loop, meaning that things that get started in the high school level, then I would put undergraduate students to work on it some more, or things that get started in the undergraduate level, we'll have high school students continue it more. So it's a two-way feedback loop system. An example of this that happened yesterday in the lab was using black hornet's nest. Yes, I said that, black hornet's nest in soap solution. We heat that up, and you could see on the left-hand side 2 yellow compounds. And in 2 hours, we had this product, red product, showing that black hornet's nest could actually be used as a catalyst for some organic chemistry. So we have fun, and we explore new and novel things at the high school and college levels. This particular project was done by a college student, is being done by a college student. So on this slide, what I want to emphasize is that one of the benefits of early research, I think if you look at the percentages of American students as you go up, let's say as you go up the STEM ladder from high school, from middle school, high school, college, graduate level, the percentage of American students decreases. And it's the case that an investment in early research and early researchers would be an investment in American students, because I think it's obvious that American students are what really populates the high school, middle school, and to some degree college levels. So investment and time spent in early research is a direct investment in American students. So I would encourage all of us to get started somewhere. The research spectrum or continuum, if you will, could be described beginning from what could be described as a cookbook experimenter, where there isn't much open-ended inquiry, there isn't much a potential for discovery, but as we go further into research, the goal, the destination, if you will, is to have students become more and more independent. One of the things that I try to emphasize to my students too is becoming an independent researcher also means you recognize the interdependence of the research process. Research on many levels are always done in the context of teams and groups and learning from each other. So while we encourage independent research, we also embrace the interdependence of the research process. Some ideas on how to begin engaging students in research. One, I'm not going to go through all of them. We're kind of getting closely on time. But one of the ideas is to create inquiry labs, meaning open-ended labs. So we don't know, both the students and the teacher doesn't know really what the answer is. We are inquiring open-ended. And you can do that using established labs. So for example, really quickly, one of the reactions that's well known in organic chemistry is making dyes from azo dyes, for example. And it's usually done using acid, hydrochloric acid. What we found is that we could actually use lemon juice, lime juice, and other acidic fruits. So we didn't know whether it will work or not, but neither myself nor the students did. But having that open-ended question to even currently established labs is one way. Another, before we get away from this slide, takes a little bit more work, but it talks to and speaks to the idea of developing collaborations, connections, and relationships between high school and college. In almost every community, there is a college, a university. It may not be close, but being able to connect with college science programs and high school and developing a relationship in which students could either during the summer do research at the college level, or college professors can come up with ideas that could be done at the high school level during the school year. Developing those relationships, I think, is key and important in helping to get started in early research. And as I said earlier, begin small. Don't overwhelm yourselves. This slide talks about the future of early research. I do have a handout on that, and you could read it in more detail, but I want to go back to the same thing that I talked about earlier, which is we have to stop thinking that we need a whole bunch of prerequisites before and in order for students to do research. Okay, research is fundamental. We go about seeking. And we could spend an entire lecture or more just about that idea. But hopefully, if you gain nothing else from this lecture, the idea that you have to, be good at math, have to take math classes, you have to do all these prerequisites before you get into the lab and do research, that is not true. In fact, research is what drives us. The curiosity is what drives us to want to read, to want to learn, to want to count. So, we need to flip that paradigm in thinking about research. Okay, I seem to have lost control of pushing this forward. Where is that? Here we go. Okay, very good. So public science, very quickly, I guess in 5 minutes, I'll have to try to get this done. So public science is a key element of early research. The way I've structured it, every student that does research with me, in addition to doing their technical report, has to do some sort of public science activity, which could include creating a research video, include writing a blog, of course, more traditionally presenting posters at research symposium in which the public is invited to come and see. Again, we'll make we'll make this lecture available so you can get connected with these examples of public science. My grade 10 chemistry class, we also engage the students there in public science. And so some of them over the years have written for a local newspaper that I'm an editor for in a section called Elements Around You. One of the things that we focus on now is having grade 10 students involved in public science announcement videos, a play on public service PSA videos. And in fact, one of the PSAs that's currently in development, actually in process, is the Michigan Fix a Leak PSA contest. This contest is actually ongoing right now. The application deadline is March 5th, and the video deadline is April 16th. So if you haven't gotten an email from me or from your school district, because I send it out pretty widely across the state, there are application forms, guidelines, and a press release in the handouts section. So you could get access to that as well. So that's something that's ongoing, and hopefully many of you who are teaching at the high school level would encourage your students to go forward. Finally, in terms of public science, one of the things we do is invite the public to listen in and on our departmental seminars lecture series. And a very good example of this was on January 28th, we had Dr. Corbett do a presentation on the safety and effectiveness of COVID. She was directly involved in the development of mRNA vaccines and the development of the Moderna vaccine. We had for that particular event over 650 attendees online, and we had at this current time over 5,300 YouTube hits on this lecture. So again, it's the whole idea of engaging the public in science. So I have a challenge to MySTEM, to MSTA, to the Math Science Centers, the Michigan Department of Education. We need to create a study action group to facilitate statewide adoption of early research. We need to imagine differently. We need to expect amazing. Franklin Roosevelt said, "We cannot always build a future for our youth, but we can build our youth for the future." And I think that's what early research does for us. I'd like to acknowledge my students for the last 25 years, high school, undergrad, grad, funding from Andrews, funding from the National Science Foundation and American Chemical Society. Thank you very much for listening.
Thank you, Dr.
Thank
Murray.
you, Dr. Murray. That was
an amazing
an
session.
amazing session.
I love the line that, we know better. Imagine different, imagine big. I think we can all embrace that challenge and find the potential in all these kids that get left out of the practice of early research and how much value that can bring to our profession. Thank you for your time. We're kind of up against our time here. Just some reminder to folks, if you are looking for that Skeech code, it's going to be Monarch. I'll type that into the chat here. Monarch is going to be your, as in the butterfly, is going to be your Skeech code. If you're looking for the handouts, you can click in the upper right-hand corner next to the chat. You should have seen those. Those handouts are now all listed there, and they'll be available when the recordings are made available to you. You'll also be able to find all those handouts if you click on any of the links over in the education sessions as well. All right. Again, I thank you, Dr. Murray, for your time, and have a great afternoon, everyone.
Thank you, Mike. Thanks, everyone.